Well, the next technology is our polymer sensors, and we have two types: a high temperature one, and the other is sort of a mid-range temperature. It goes up to 85 degrees C, and the one on the bottom goes up to 150 degrees C. The one on the top has an integrated CMOS circuit, which provides a voltage output, and the one on the bottom is a capacitance change. And these are somewhat similar to aluminum oxide, but rather than the aluminum oxide substrate, it's a proprietary polymer. There's some people in the industry that say that these sensors were discovered by accident, that somebody was using polyimide as a conformal coating on circuit boards, and they noticed when they were testing the circuit boards that there was a variation due to what they originally thought was temperature, but when they did some further studies in environmental chambers, they found that they had almost a direct proportionality to humidity, and they figured out that the polyimide, if cured under certain conditions, could actually become a humidity sensor. So a lot of it was derived from that. I don't know how true that story is, but that's that's the story I heard. Well, in any regard, these sensors will put out a signal, and they're designed for higher levels. We calibrate them by putting them in a test chamber, a two-pressure chamber referenced to a chilled mirror. On our lower temperature sensors, we only have to do a two-point calibration, and that sensor uses a mathematical relationship for temperature compensation. So by measuring the temperature, we just are running an equation to correct the sensors to read the correct relative humidity. For the high temperature, we plot out essentially a matrix. We run the sensor at 5 different humidity values at 3 different temperatures, and essentially plot that into the unit's microprocessor as a lookup table. So it becomes a calibrated system over that full array of temperature and humidity. And these are typically just assembled in a stainless steel probe with a header that puts out a linear 4 to 20 milliamp signal. And they're using a whole host of applications, everything from ambient air to cement making to food processing, where, for example, drying nuts or even curing the adhesive on sandpaper, might be applied to, these sensors might be applied to those process controls. The next technology is our TDLAS, which is the laser. And our laser has been primarily designed for moisture and natural gas. However, we've applied it to a number of different applications, including furnaces and now a nuclear application where it's measuring CO2 in a containment. So these are configured in a complete sampling system, or we now have also a benchtop version of this, and they carry the explosion-proof certifications. They'll put out 4 to 20 milliamp as well as the digital interface as well, serial interface with Modbus. The principle behind this is that we have a stainless steel tube, essentially, and inside that stainless steel, it's actually polished stainless steel, so it's a very smooth surface. And hermetically sealed away from that is a laser emitting unit, a diode laser, and there's an optical window made out of quartz. So the laser beam is shot down to a mirror. The mirror consists of it's gold-plated, and then on top of the gold is a silicon coating, which is essentially like glass. And that mirror is only used to double the path length. So as the laser is tuned or ramped through a narrow band frequency in the infrared, there's a particular frequency where water absorbs the energy. The water molecule has a unique vibrational and rotational characteristic that absorbs that photonic energy. So you're getting, at that particular frequency, less photons than what you put into the system. And the longer the path length, the more absorption or loss of signal you'll get if there's water in it. So by having a constant length, and we're able to look at the absorption characteristic and determine that, yes, there's water in there, but not only that, how much water, by looking at the loss of signal or the absorption. The laser is actually scanned 3 times a second. We take 3 measurements every second. And the base of the laser is precisely temperature controlled. There are 2 ways to change the frequency: change the temperature of the laser or inject current into it. So we're ramping the laser by injecting current into the laser diode, and that essentially changes its frequency. At the same time, we measure the pressure and the temperature of this system. So the nice thing about that system, let me just go back for a second, is that it's completely inert, in the sense that there isn't a sensing surface in the wetted flow of the gas. There's really nothing to wear or degrade over time. It's a fully non-contact system, and it's a very fast-acting system. This graph just shows the absorption peak at various concentrations, and so we can see that there's a direct proportionality to the height of the peak, centered right around 77 on this graph, and the concentration in parts per million. And this is what's called a 2F or raw signal. So when we calibrate these systems, we're recording that peak height versus the concentration and using that as a lookup table for the system. So one nice thing about this system is it's very, very repeatable. This is just a graph that shows the system dry out. Here we have a step change from about 5,500 part per million to 12 part per million, and that step change occurred in 50 seconds, and that's inclusive of the sampling system and the volume of the absorption system. So by comparison to other technologies, this is much, much faster. It's magnitudes faster. If this same step change were aluminum oxide, it would take hours, or close to an hour, let's say, to fully stabilize at the same step change. A chilled mirror would probably take 30, 40 minutes, if not an hour as well. One of our customers wanted to test a process upset. So in the field, they injected water into a natural gas system, and the system immediately spiked and returned back to normal, fully back to the original value within 7 minutes and within 2 ppm of the original reading in 2 minutes. So again, if this were other technologies, this would take several hours to recover, if not overnight. Now, the Aurora system that is patented in the sense of our pressure and temperature compensation. So in order to give greater precision, we vary the temperature and pressure and record that data into a matrix as well. Absorption, as you increase the pressure, you get this phenomenon called pressure broadening. And that's because you have more interactions between water itself, between water molecules, as well as the other molecules. So you don't get the predicted absorption that you normally would because of this collision broadening. And temperature has a very similar effect. So we're able to compensate for that or adjust for that by ramping the system through pressure and temperature and then storing that data into the unit's memory as a lookup table. And it works very effectively to give us very good precision. For ultra-low levels, we have the Aurora-Trace, and that was launched last year. So the standard Aurora goes down to about 5 parts per million as its lower detection level. And this Aurora-Trace is able to go down to virtually pretty close to 0, but no system gets to 0. It will go down to 50 part per billion fairly consistently. And one of the ways it does that is there are really 2 aspects that it enables it to give sort of this, what we call high definition laser absorption. One is we apply a vacuum to it, and the vacuum has the opposite effect as pressure broadening. We call it pressure sharpening. And the other method is to increase the path length. We have a very long path length by using a finesse cell. And what the finesse cell does is it bounces the light back and forth. So that's just sort of a graphic of the finesse cell. You'll also see the name Harriet cell used quite a lot. Harriet is a specific type of finesse cell. But essentially the light enters into this tube, and with specially curved mirrors, it bounces back and forth. We're able, in a 1 meter length, to effectively get a 30-meter length. And the longer we make the path length, the more opportunities for the water, for the light to be absorbed by the water. That finesse cell is also temperature sensitive, so we precisely control the temperature by a heating jacket that goes around the multitask cell. So the effect of the pressure broadening is shown on this slide, and the dotted line is at atmospheric pressure. The same gas under 2.5 psia is the red line, and you can see that there's a lot more detail on the red line than what you had on the dotted black line. And that detail comes out as sort of like looking at a high-definition television versus a conventional television. You're seeing much more detail. There's actually about 5 discernible peaks that come out under the vacuum condition, and there's one sort of broadened peak that comes out under the atmospheric condition that's attributable to water. This is particularly interesting when you're looking at low levels because many of the hydrocarbons, such as methane and ethane, have co-absorption characteristics at these very low levels, and under higher moisture concentrations, their absorption values are negligible. But when we're dealing in part per million levels, they become more significant. So we're able to get rid of those effects or negate those effects by applying a vacuum to this system. And this is just another graph of showing that at various concentrations. Now, there are 2 peaks in this one that we identify, and we actually use both peaks in the assessment of the water concentration. So again, we get a very sharp, narrow peak attributable to water, or actually 2 peaks, by operating this system under vacuum. Another method of doing that is differential spectroscopy, where you take the gas sample and dry it through a getter or a zero gas generator, a drying system, and you essentially subtract the effect of the zero gas from the process gas. But that bump attributable, or that peak on the zero gas, is ambiguous. Where is that peak coming from? Is it water, or is it due to co-absorbers? You can never know. And the other issue with this is that you have to take the measurement offline to dry out the sample. With the vacuum system, the system can go online 24/7. And should the vacuum pump ever fail, there's a pressure sensor that monitors it. You'll get an alarm. With this, you're reliant on having a good, effective purifier, and that purifier is many times a finite column. So as that absorbs water and breaks through, you don't know until you see a peak on the zero gas. So we feel that there's several advantages to the vacuum system versus the differential spectroscopy that's traditionally been used. And this is just data showing the response time of the trace, the Aurora-Trace, as compared to a chilled mirror. Notice that it's on a logarithmic or an exponential scale on the y-axis, but these were 3 different units that dry down. One of them was at a slightly faster flow rate, and the T90 here is less than 2 minutes. So again, very fast response times as compared to other technologies. And those are just step changes on the Aurora. And again, a similar process on our calibration systems. We do quite a bit of automation. These units have digital interfaces that are bussed in, and the calibration system is completely automated for these laser systems. We're often calibrating in natural gas, or if it's a gas mixture that deviates from what we consider to be standard natural gas, we can reproduce that mixture in our gas by mixing pure gases together and using that as the background gas for calibration. We feel it's always better to calibrate in something close to the process gas you're using than to calibrate it in an inert gas. I'm just going to run through the applications we get into pretty quick, as starting to get close to the end point here. But a lot of what we sell is applied to refineries and petrochemical. These are the feedstocks, but we also get involved in catalytic cracking, or CCR, on the H2 recycle gas, ethylene production, alkylation and isomerization. And very often these systems are put together with fairly elaborate sampling systems. For liquids, for example, and on these sampling systems, we have stainless steel tubing inside a copper tube, and fluid is run through the copper tube to cool the gas sample, or the liquid sample, prior to the sensor. In other words, the liquids are hot, so we have to cool the liquid down to the operating temperature of the sensor. Sensor is housed in an explosion-proof enclosure and then connected into the analyzer in the safe zone. So in this application, we're directly measuring the moisture concentration in liquid feedstocks. And very often our analyzers are looking at multiple channels. Our standard analyzer can look at 6 channels simultaneously. Of course, air separation, in petrochemical, it's taking crude oil essentially as your core product and distilling it. In the air business or gas business, you start with gases and then you cryogenically cool down and separate the different components. So very often we're looking at that process and purities. The dryers that have to cool those systems are often pressure swing absorption, and we'll be measuring off those. Semiconductor industry, of course, just in the environmental clean rooms, product testing, and in the manufacturing process, very often they're wanting in the silicon wafer level to get down to sub 1 part per million or even parts per billion levels. We do quite a bit in natural gas, and it's everything from transmission gas to LNG production. Our laser technology seems to be the technology of choice in this application, but we still apply a lot of the aluminum oxide sensor into natural gas. In power generation, we're looking at gas turbines, anti-icing and emission controls, fuel quality going into the turbine, and of course in hydrogen-cooled generators and oil-filled transformers and sulfur hexafluoride switchgear. The pharmaceutical, again, a lot of environmental type of testing, process testing, very regulated industry that requires a lot of calibration as well and documentation. Compressed air is, in every plant, it's sort of the fourth utility. Of course, you have steam, electricity, water. Well, maybe the fifth utility, natural gas is maybe considered another one. And compressed air, it's used from everything from spray painting to purge gas or TIG welding to just instrumentation air. So we do quite a bit with that. Metal processing, we get involved in blast furnaces, in atmospheric control furnaces, annealing, and galvanization. So all of the sheet metal, the galvanized sheet metal that's used in automotive, that's processed in a atmospheric controlled furnace where moisture essentially is controlled. They're trying to get down to negative 60 degrees C or lower in those applications. Same thing with plastics. Plastic resin under pressure and temperature, any water in that will turn to steam and cause bubbles or splay in the finished product. So it's limiting the amount of moisture in the blow molding or injection molding process. We do quite a bit in automotive and engine testing, both on the intake side and the exhaust side. We're one of the few companies that can measure moisture in exhaust air from an automobile or a combustion engine. And it's similar in aerospace. We do everything from de-icing studies to antennas and waveguide, and quite a bit of engine testing as well. The refrigeration industry and heat exchanger, wherever there's an air side or gas side heat exchanger, the amount of moisture plays a big role in that efficiency. So we're doing a lot of performance testing with our chilled mirror equipment, as well as in environmental chambers. And as we kind of wrap this up, we've talked about the instrumentation, but it's often very important, and as important, to have a good sampling system, to have good measurement integrity. So we've got a lot of experience with sampling systems, and we do things like stream switching or solenoid valves for purging in cal gases, or just the regular cleanup of depressurizing a gas, filtering the gas or liquid, and regulating the flow through the sensor system. Throughout this, we've mentioned a number of our test and calibration facilities. We've put big premium and investment into automating much of this. We do our own in-house testing. And we also do product training, both either at your facility, we'll send out an engineer or a technician to give you hands-on training, or you can come to our facility here in Boston, the Boston area, for hands-on training at our facility as well. So with that, that's sort of the conclusion. We ran a little bit over time, but certainly I'm open for any questions that anyone has.
Yeah, we might be able to squeeze in a couple. Looked like another one came through was someone said after observing a step change in the process from negative 40 Celsius to 20 Celsius, we have 20 Celsius for an extended period of time, and wanted to know what the anticipated dry down period is for a polymer sensor to accurately measure again at we get negative. I think that's about it for the questions that come in. Everyone, we appreciate you taking the time. Again, we're going to make this webinar available at RAECO.com/training. There you can go and find many of our other webinars that we've hosted. So hope you found this worthwhile, Ken. We really appreciate the time, appreciate the information. If you come up with our questions, be sure to, you can email me at tom@raeco.com, and we can point you in the right direction. So thanks again, and everybody enjoy the rest of your day.